is recording. Okay, content objectives. We're doing 3-1 conjectures and counterexamples. I realize those are new words. They actually have pretty simple meanings, but they are new words. Conjectures and counterexamples. Students analyze conjectures by using inductive reasoning and disprove conjectures by using counterexamples. Like I said, the concept, I know these words sound big, but the concepts are actually really simple, which is nice. Use the pattern shown to make a prediction. Complete each statement. Okay, so here for number 1, it says 3 squared is 9, 5 squared is 25, 11 squared is 121, 17 squared is 289. And then it makes, this is a conjecture. The square of an odd number is and, so we use this to come up with a conclusion. If we square an odd number, all of these are odd numbers. So our conjecture is that based on this pattern, the square of an odd number is an odd number. Okay, then the next pattern, we see 4 squared, 8 squared, 14 squared, and 20 squared. The square of an even number is a blank number. Let's see. Looks like these are all even numbers. Even numbers. Again, this is a conjecture. We're looking at a pattern and coming up with a conclusion. When we look at a pattern and come up with a conclusion like that, it is called inductive reasoning. So we're using inductive reasoning. Okay, next one, looking at this pattern, 2 plus 5, 15 plus 4, 22 plus 13. The sum of an odd number and an even number is an blank number. So it looks like the sum of an odd and an even, it comes out to an odd number. Odd and an even comes out to an odd. Even it comes out to an odd. So it looks like it always comes out to an odd number. And here is another pattern. They're multiplying numbers by 10, and they say the product of any number in 10 is a number that ends in, it looks like they all end in 0. Okay, and then number 5, you may have seen this before. To determine if a number is divisible by 3, you can actually add those two. So to see if 12 is divisible by 3, you can actually add 1 plus 2. And if this value is divisible by 3, then 12 is divisible by 3. So for 24, you can add 2 plus 4 to get 6. And if 6 is divisible by 3, you know that 24 is divisible by 3. And this 36, 3 plus 6 equals 9. And if 9 is divisible by 3, then 36 is divisible by 3, and it's just a little hack. If you want to see if 132 is divisible by 3, just add 1 plus 3 plus 2, and if 6 is divisible by 3, then this is divisible by 3. So if the sum of the digits of a number is divisible by 3, then the original number is divisible by 3. Okay, so now it's going to start explaining some of the vocabulary we've been using. It's this right here, inductive reasoning is the process of reaching a conclusion based on a pattern. So we've been looking at patterns of examples. When you assume that an observed pattern will continue, you are implying inductive reasoning. You can use inductive reasoning to make an educated guess based on known information in specific examples. This educated guess is known as a conjecture. So a conjecture, educated guess based on a pattern. Okay, so now we're going to look at some examples and then create a conjecture and then use that conjecture to make a prediction about what will happen next. So write a conjecture that describes a pattern, then use your conjecture to find the next term in the sequence. So here it has appointment times, 8:30, 9:15, 10 o'clock, 10:45. looking at those, it looks like there is an appointment every 45 minutes. So our conjecture is each appointment is 45 minutes after the previous apt. Okay, and then predicting the next appointment time, well then the next appointment time would be 11:30 a.m., 45 minutes after the previous one. Pretty easy. That's what we're doing today. Okay, next. Write a conjecture that describes the pattern in the sequence, then use your conjecture to find the next term in the sequence. So here we have 1/2, 1, 2, 4. It looks like it's doubling each time. Each term is doubling. So the next number is 2 times the previous number. So the next term would then be 8. Okay, ready for the next page? No? Next example, top of the next page. There's an example here and then a separate example here. So example 2, make a conjecture about the sum of squares of 2 consecutive numbers. So I know that might seem confusing, but what it means is sum of squares of 2 consecutive numbers. So 1 squared plus 2 squared, or 2 squared plus 3 squared. So this would be 1 plus 4, it would be 5. 4 plus 9 would be 13. I could give more examples, but what will happen is it'll always equal an odd number. So the conjecture is sum of 2 squares is equal to an odd number. Okay, next, make a conjecture about the sum of 2 odd numbers. So what we're going to do is create a list of odd numbers. So 1 plus 3, or 3 plus 5, or 7 plus 9. And then we'll solve them and see if there's any conclusions we can come up with. So this equals 4, this equals 8, this equals 16. It looks like they're all coming out to even numbers. So the sum of 2 odd numbers is an even number. Okay, so now we're going to do something similar but with actual data. So it says gas prices. The table shows the average price of gasoline in the United States for the years 2010 to 2018. Make a conjecture about the price of gas in 2019. Explain how this conjecture is supported by the data given. Okay, so looking at this, we're going to be looking at whether gas prices are increasing or decreasing, so that way we can make a prediction. I noticed that it's increasing and then it starts decreasing again, so maybe I need to look at this in more detail. It looks like from 2010 to 2013, it is increasing. Then it starts decreasing, and then it starts increasing again. Increasing, decreasing, increasing. So based on this pattern, I think it's going to continue increasing in the year 2019. So our conjecture, remember, it doesn't even have to be right, it's just based on the data, this is what we're predicting. In 2019, the price of gas will continue increasing. Okay, next example. Again, we're looking at real data. The owner of an ice cream shop collected data on the total sales for the first 5 months that the shop was open. Make a conjecture about the sales total in the 6th month, so 6th month. Explain how the conjecture is supported by the data given. Okay, in order to make a prediction, we have to look at what's already happened. Let's see, from this month to this month, it would be plus 200. Then from 700 to 950, plus 250. Looks like plus 300 here. And then from 1,250 to 1,600, that would be plus 350. So my guess, based on this pattern, each month they're making $50 more than the last one. Or I mean, like, well, so plus 200, plus 250, plus 300, plus 350. So I'm thinking plus 400 right here, based on that pattern. So then I would guess they'd make $2,000 in the 6th month. So my conjecture is the sales in month 6 will be $2,000. The sales in month 6 will be $2,000. And explain, I could have us like go through a whole like paragraph explanation, but pretty much based on the pattern, they should add $400 next. What's wrong? 200, 250, 300, 350, 400. Sorry. Okay, so a conjecture is an educated guess based on a pattern, but it doesn't always have to be right. So sometimes conjectures will be wrong, and you have to use a counterexample to prove it wrong. So to show that a conjecture is true for all cases, you must prove it. It only takes one example that contradicts the conjecture, however, to show that the conjecture is not always true. This example is called a counterexample. I'm going to write that bigger. Counterexample, because that's our next like keyword. It can be a number, a drawing, or a statement. It says, to show a conjecture is true for all cases, you must prove it. It only takes one example that contradicts the conjecture. However, to show the conjecture is not always true. This example is called a counterexample. It can be a number, drawing, or a statement. Period. Okay, just have half a page more. Ready, set, next. Counterexample, yes. So pretty much a counterexample proves a conjecture is false. That's the gist. Okay, next.
Okay, go back.
Oh.
Jeez, I can't see.
Okay, next. Okay, find a counterexample to show that each conjecture is false. So you're looking for an example that would prove this statement wrong. It says if n is a real number, then negative n is a negative number. Well, what if n is a negative number to begin with? Then negative n would actually be positive. So what we're doing is we're thinking of an example like, what if n is negative 4, then negative n would be negative 4, which is a positive number. So this would be false, which they tell us is false, but. Okay, then B. If angle ABC is congruent to angle DBE, then ABC and DBE are vertical angles. Well, vertical angles are equal. However, just because these angles are equal doesn't mean they're vertical angles. So just to remind you, vertical angles are when you have like opposite angles that are the same measure. Vertical angles are equal. But they're saying just because they're congruent, they're vertical angles, and that is not true. So we're going to use a drawing for this. So let's say that angle ABC is 46 degrees, and let's say angle DBE is also 46 degrees. Well, these are congruent, but they're not vertical angles. So angle ABC is congruent to angle DBE in our drawing, but they are not vertical angles. So this conjecture is false. Okay, so it says, find a counterexample to show that the conjecture is false. If n is a real number, then 1 over n is less than n. Select all that apply. So these are options, and we want things that prove this false. So if I put 1 over negative 3, is that less than negative 3? Well, negative 1/3 would actually be greater than negative 3. Just kind of like let that say, negative 1/3 would be greater than negative 3 because negative 3 would be more negative. So this would be a counterexample, and there's more than one option here. One over, if n was 1/4, 1 divided by 1/4 would be 4, and 4 is not less than 1/4. So this would also be a counterexample. For this next one, 1 over 1, would that be less than 1? No. It would be equal to, so this is a counterexample. D, 1 over 5, would that be less than 5? Yes, that works. And then for 100, 1 over 100, is that less than 100? Yes. So it just wanted the ones that are prove this false, so those are our answers. Okay, just going to put this off to the side. If a line intersects a segment at its midpoint, so a segment right here, a line intersects that segment at the midpoint, so let's just draw a line. And then midpoint means this will be equal to this. Then the line is perpendicular to the segment. Well, in my drawing right here, no, it's not perpendicular. It could be, but not always. So, false. And this is an example. Let's see, the line is not always perpendicular. And we're done. Okay, so that's the gist. A conjecture is an educated guess based on a pattern. A counterexample is something that proves that conjecture false. And that's the gist. Okay, so now you have the rest of class to do the homework. I'm assuming the homework will be very short since there's not a lot of math solving. It's just like reasoning, true, false, that kind of thing. Once you finish the homework, then work on Alex. If you need to finish the test or take the test, that is your priority, and you need to go on to McGraw Hill to take the test. Questions? Everybody kind of know where they're at? Okay, I'm going to end this recording. Go ahead and grab a laptop. I'm going to enable the homework.